Good morning, everyone. You're all doing well. I had a couple people email me last night, right before the homework was closing, saying that there had been some issues with the Mastering Chemistry website. And that was not just for your class. I also got it in my 130 class. So I will be extending the due date on that homework until probably just move it until this Sunday. If you've already done it, then you don't have to worry about it. If you weren't able to complete it, you'll have some more time to get that done. And I'll send you all a follow-up email about that. So let me share my screen here in just a minute. Okay, so we're in week 8. So we're pretty much halfway through the semester. We're almost halfway through the information. We will be at the end of this week. Your second test will cover chapter 5, 7, and 9. That's going to be opening this Sunday and completed by Monday. Same format that you guys are used to. It's going to cover all the nomenclature stuff, the electron stuff, and then chemical bonding, which we'll get into today. So I'll send you, or I'll give you a couple other reminders, but just make sure that you've got that on your radar, that you do have a test that you want to complete this Sunday/Monday. So the next chapter we're going into is chapter 10. So again, kind of hopping around. We did 5 and then 9 and 10. We're going to go back to 6, 7, and 8 after all this. This whole chapter involves chemical bonding. So we have working knowledge now of nomenclature, naming, and compounds. We understand kind of why things come together the way that they do. You've got an idea of what's happening with the electrons and the valence electrons and electron configurations. And so now we're going to put those two concepts together and start to make visual 2-dimensional and 3-dimensional structures of these compounds. So in chemistry, we have these things called bonding theories, and bonding theories are a system of ideas that help us predict how atoms will bond together within a compound. So, you know, CO2, why carbon is in the center and the oxygens are on the sides, and how strong those bonds are, all that sort of stuff we can predict using these theories. They help us to determine like why certain atoms come together and certain atoms don't come together. They can let us know, you know, why table salt is NaCl and not NaCl2. You kind of already have working knowledge of that because you know that this has 1 valence electron, this has 7 valence electrons, so it's just going to transfer it. But we're going to get to see that in a visual way. Also let us know that water is H2O, not H3O, why that's the case. And then we're going to make all of these, we're going to do it first with Lewis dot structures and make a 2-dimensional structure. And then we're going to try through the computer to explain a 3-dimensional structure. So what these actually look like in real space. So Lewis theory came from a guy named Lewis, who was an American chemist. And what he did was when combining atoms together in a compound, he would represent electrons as dots. And he would put them around whatever the element is he was talking about. And they were called dot structures. So this is that part of chapter 5 lab that I said, just skip over it. We're going to talk about it now. So there's a lot of predictability power and just putting these silly little dots around the name. You can predict why certain things will come together, why certain configurations are more stable. There are more advanced theories outside of Lewis's theory, but this will work for us in this class. So we'll stick with that. So in Lewis theory, the valence electrons of any main group element are represented as dots around the element's symbol. If you're in group 2, remember you have 2 valence electrons. If you're in group 8, you have a full 8 valence electrons, except for helium. Remember, helium only has 2 valence electrons in its outermost shell, but that is stable for helium. So oxygen, okay, if we write out our electron configuration, it would be 1s2, 2s2, 2p4. When looking at valence electrons, we just look at the highest number. So the 2s here, there's a 2 in this 2s and there's 4 in this 2p for a total of 6 valence electrons. Do you want to draw that thing out? Probably not. You probably just want to go to your periodic chart and see that oxygen sits in column 6, 6 valence electrons, easy peasy. When drawing the Lewis dot structure, it would look something like this. So I would write the symbol for oxygen, and then I'm going to put all those little dots around it. And I want you to think about there being 4 quadrants around the element. So a top, a right, a bottom, and a left. Each quadrant will hold a maximum of 2 electrons. So when we're full, there would be 8 electrons, right? 4 quadrants, 2 electrons each for a total of 8 electrons. Oxygen, because it only has 6 valence electrons, I can actually only fill in 6 of those 8 slots. You always fill them in singularly first because electrons have a negative charge. So they want to get as far away from each other as they can. So I'm going to put a dot here, a dot here, a dot here, a dot here, and then I'm going to go back and double up. That's why oxygen's configuration or its Lewis dot structure looks like this as opposed to this. We wouldn't want to do this. Oxygen and go 2 on this side, 2 on this side, and 2 on this side, and then leave this side sort of hanging. Why? Because it's lopsided. So we don't like that. We want to fill singularly first and then go in and double up. Now, oxygen has more than 6 electrons, right? It's got these 2 in that inner onion layer, but we don't worry about those. They don't have anything to do with bonding. The only thing that bonds are the outermost electrons, okay? So sulfur, if I was to do the Lewis dot structure for sulfur, well, sulfur is also in column 6. So it also has 6 valence electrons. So its dot structure is going to look very similar to oxygen's. It happens to have one more completed onion layer inside this, but the outer electrons that you get to play around with are the same. So sulfur and oxygen behave very similarly. Let's look at some of the other Lewis dot structures. So each dot represents a valence electron, fill the dots in singularly, and then pair them up. So here are all of the Lewis structures for the elements in the second row. So we can see lithium is in column 1, it gets 1 valence electron. Beryllium's in column 2, 2 valence electrons. We continue on. You can see carbon here has 4 because it's in column 4. We fill those in singularly, then we would go ahead and double them up. So I wouldn't have 2 here and 2 here. That would be, it wouldn't be very symmetrical. All the way over to neon, which is a noble gas. And it's kind of like these noble gases are magical, right? Everything wants to be like them. Why? Because it has this thing called an octet. Oct, like octagon for 8. So it has 8 electrons in its outermost shell. It is very, very stable. So fluorine, right, is really close to having 8. It's got 7. If we just added 1 more electron, it would become like this 8 octet noble gas. Well, what does fluorine usually form as far as its charge is concerned? It forms a -1, right? -1 means we add an electron. So don't get valence electrons and charge confused. This is a +1, this is a 2+, 3+, well, not really 3+. This is, don't worry about that one, that's either or. 3-, 2-, and then neutral, right? Add 2 electrons, fill 2 slots. Add 3 electrons, fill 3 spots so that we can all get to this octet. So the Lewis dot structure for phosphorus. Phosphorus sits underneath nitrogen. It's in column 5, so it would have 5 valence electrons. So its Lewis structure is very similar to nitrogen, right? The only difference really being that we changed the symbol. Helium is an exception to the rule, and that when we're drawing helium, we put the 2 dots on one side. This is known as a duet. A duet is particularly stable for very, very small things. So like hydrogen likes to form a duet, helium likes to form a duet, lithium can form a duet. Everything else though wants an octet. So for those tiny guys, give it a duet, put the 2 dots on the same. You don't fill it singularly. So we would never do helium like this, where we put a dot in this quadrant and then we put a dot in this quadrant over here. With helium, we're just dealing with one quadrant or one area. So on the same side. So Lewis theory of chemical bonding. In Lewis theory, a chemical bond involves either a sharing or a transfer of electrons. So remember, when we're transferring an electron, we're talking about an ionic bond, okay? And remember, another way to think of that is a metal, which is a cation, and a nonmetal, which is the anion. When I say cation, I mean a positively charged thing and a negatively charged thing. The positive thing is getting rid of the electron. The negative thing is taking the electron on, and then their charge differential makes them stick together. In a covalent bond, we share electrons, okay? These involve nonmetals. A lot of our Lewis dot structures are going to be spent here with covalent bonding, not so much with ionic bonding. We'll do a couple with ionic, but either approach, whether we're transferring the electron or we're sharing the electrons, we will get the same result, which is to create a stable electron configuration. And when I say stable electron configuration, I mean that we're trying to create an octet or a duet for the small things. Okay, we're trying to get those full shells. So a stable configuration consists of 8 electrons in the outermost valence shell, which we call an octet. And then the few exceptions, there are more exceptions to the octet than this, but group elements like hydrogen, lithium, and then even beryllium, they're okay with a duet in their outermost shell. So let's first work with Lewis structures on ionic compounds. This isn't going to be quite as big of a concept as the other one with covalent, but we'll still review it. So when we have a metal and it bonds with a nonmetal, electrons are transferred. That means the electron goes from the metal to the nonmetal. It creates a cation and an anion, or a charge differential, and then the two are attracted to each other and they stick together to form this 3-dimensional lattice structure. In Lewis theory, we represent this moving electron from the metal to the nonmetal. I'll show you here. So if I've got potassium and chlorine, if you're doing an ionic compound Lewis structure, you'll want to draw the metal with all of its valence electrons. So potassium is in column 1, so we give it 1 dot. Chlorine is in column 7, so we give it 7 dots. So you might already be able to see from here like what makes sense to get those complete onion layers. If this potassium gets rid of this, it will have a complete shell on the previous row, right? So potassium will jump back to the configuration of, hold on 1 second. Okay. Potassium will have the configuration of argon. Now that electron doesn't just disappear, it actually gets transferred and gets filled in over here, right? Now chlorine has a complete shell and chlorine is behaving more like argon. So we transferred it over, but there's a change that happens to the charge when we move the electron, right? So when I get rid of this electron, we drop it here, but we have to add a plus charge. When I add the electron, I have to put the thing in brackets and give it a minus charge. You don't bracket the metal, you bracket the nonmetal because you want to encompass all the dots. They don't draw the dots from the previous set on the metal. It's just inferred or assumed that there are in fact 8 valence electrons from, if we're in potassium, traditionally we're in row 4, but it has the complete dots from row 3. So we got a positive and a negative, and what do? They stick together. So by transferring one of these electrons, they were able to create octets. Now both of them have stable electron shells. Let's look at this over here. So I've got magnesium and oxygen. Magnesium has 2 of these electrons. So do we want to add 6 more electrons? No, that's too much. Instead, we're going to strip these 2 electrons away. And then look, there's an oxygen over here. This has 6 electrons. Are we going to strip the 6 electrons away? No, what we're going to do is we're going to add those 2 electrons over here. That's going to drop the charge here to a 2+, because it's going to increase the charge to 2+ because we dropped 2 electrons. And then over here, we added 2 electrons, so we have a 2- charge. Now these 2 things stick together. If this feels like, wow, this is a lot of work for what I already know how to do, that's why we don't spend a whole lot of time on it. I think it's a little bit, it's a little overkill with the ionic stuff. Just one more to show you. Sodium here has 1 valence electron because it's in column 1. Sulfur has 6 valence electrons because it's in column 6. So if I move this electron here over to, sorry, not sodium, sulfur. If I move sodium and sulfur, if I move the electron from the sodium to the sulfur, this will have a complete shell. So this thing is happy. This one has 1, 2, 3, 4, 5, 6, 7 now. Is it happy? It doesn't have the octet yet. So what needs to happen is another sodium with another valence electron needs to be able to offer it. So what we end up getting is 2 sodiums giving up 1 electron each, and the sulfur eating those 2 electrons. And what do we end up getting? Na2S. And it would look something like this, the sulfur sitting sort of in between the 2 sodiums. Now, doesn't that seem like a lot of work for what we already know how to do, which is Na+, S2-, flip-flop, we get Na2S. Right, so if you want to draw it out like this and be like, well, that's why there's 2 sodiums, you can. I tend to just stick with this. It's a little bit easier. But the really important thing with Lewis structures is looking at when electrons get shared. Okay, so when we have 2 nonmetals, 2 or more nonmetals, they are going to, instead of transferring the electron, they're going to share the electron because both of them are low on electrons and they want to have more. So they're going to share the electrons to try and reach an octet and or a duet. So if we look at hydrogen and oxygen here, and I'm going to actually draw this over here so I have a little bit more freedom. Oh, that was my daughter. Okay, so hydrogen has 1 valence electron and oxygen has 6 valence electrons. So it looks something like this. There's 2 quadrants that are missing an electron. So this is different than ionic. And in ionic, we would say, oh, well, let's just take this electron and move it over here. But why doesn't that work? Because then hydrogen has no electrons. Like, look at where hydrogen is on the periodic chart. If you drop its electron, it has 0 electrons. It is not happy that way. So instead, what needs to happen is these 2 sort of share these electrons. So they, like this hydrogen says, okay, I'm going to move over a little bit. And I don't want to give you my electron because I need it, but I'm going to sort of put it here so we can both like access both of these electrons. Let me move this other guy over, and oxygen's like, okay, that's fine. I'll share my electron as well. And so now what we have is hydrogen now has access to 2 electrons. This oxygen has access to 1, 2, 3, 4, 5, 6, 7 7 right now. So in actuality, another hydrogen needs to come along with its valence electron and sort of stick it there so that they can share it. So the hydrogens have access to 2 electrons. And remember, hydrogen likes 2 electrons, or the duet. Okay, hydrogen doesn't need 8. What's happening with oxygen? Well, by making this sort of symbiotic relationship, oxygen has its original 6, and it also has access. We kind of lost an electron in there, didn't we? To 8 electrons, right? These 4, and then the 2 here and the 2 here. So by sharing, everyone was able to get their octet and or duet. So there we can see oxygens and the hydrogens. Everybody's happy here. A little bit better of a drawing. There's our hydrogen with its duet, and there's the oxygen with its octet. Transferring wouldn't work. If hydrogen was to just give the oxygen its electron, both the hydrogens wouldn't have any electrons. Their outermost shell would not be satisfied. So you're always going to be trying to like share, move things together in such a way that everybody gets these octets and or duets. And there is an actual system to how you do it, and I will show you that in a little bit. But I do want to identify a couple of points on one of these structures. So the electrons that are being shared are called bonding pair electrons. So these 2 electrons here and these 2 electrons here are called bonding pair electrons. Bonding pair because there's 2 of them. The other things, the other electrons that are on the central atom that aren't included in any sort of bonding, or they're kind of partnerless, these are called lone pair of electrons. Okay, so this has 2 lone pairs of electrons and then 2 bonded pairs of electrons. To make it easier for the reader, a lot of times those bonding pairs, they will draw as a line. So you can see here, they've taken this here and this here, and they've made it a straight line or a stick. And that just makes it a little easier to differentiate between our bonding pairs, what's connecting 2 things, and then the lone pairs, which are just there because they need to create an octet on the central atom. So I will be drawing these as bars. A single bar is equal to 2 electrons. Okay, a double bar, which is known as a double bond, is equal to 4 electrons, and a triple bond, which is 3 bars, is equal to 6 electrons. And we will talk about when you want to do double and triple bonds, but for now, just know that each of the bars is symbolic of 2 electrons. So now we can explain why the diatomics do the things that they do. So think about chlorine. Chlorine on its own has 7 valence electrons. It's really close to being a full octet. When chlorine is just by itself, it will combine with another chlorine to create an octet, because we can see this chlorine here brought these 7 electrons, and this chlorine here brought these 7 electrons. And when you put them together, now each of them has access to 8 electrons. Chlorine here has 8, chlorine here has 8. So this is more stable than chlorine existing on its own. You would probably see it drawn more like this, where those 2 electrons in the center are represented with a bar. Is this true for other diatomics? Yes. Let's look at hydrogen. Hydrogen is a diatomic. Hydrogen is in column 1, so it has 1 valence electron. Not stable. But if I stick it with another hydrogen, each hydrogen brings its own electron to form a duet. So they each have access to 2 electrons. Now they're stable. That's why they stick to themselves. Oxygen does the same thing. Oxygen is a diatomic. A little different with oxygen though. Oxygen has 6 electrons. So if I stick it together and share one of these electrons, this oxygen here has access, to 2, 4, 6. This oxygen has access to 2, 4, 6, 8. So in this current structure, this guy is not happy. This guy is good. This guy is not happy. So what needs to happen is the oxygen with the more electrons needs to decide to share. So it takes these and it moves them into the center. So now we have what's known as a double bond. There's the same number of electrons. This oxygen has access to 8, and this oxygen also has access to 8, or we get a structure that looks like this with double bonds. And again, I will explain a little bit more how these electrons get distributed and where the dots go and everything. But for now, just sort of generally stick with me on it. So double bonding gives us an octet for each. What about nitrogen? Nitrogen, each one brings 5 electrons. So if I stick them together, both of them are short. This nitrogen has 6 and this nitrogen has 6. So what we need to do is take, this pair and drop it in here. That would give this access to this, that would give this access to 8, but the other guy would only have access to 6. So we actually have to take another pair and drop it in like this. So both of these get dropped in and we get what's known as a triple bond. I haven't changed the number of electrons. There's still only 10 electrons, but they're distributed in such a way that how many does this nitrogen have access to now? 2, 4, 6, 8, and this nitrogen also has 2, 4, 6, 8. So it's kind of a game of moving things around so that everybody gets what they need. Couple things to note about double bonds and triple bonds. In general, double bonds are shorter and stronger than single bonds, and triple bonds are shorter and stronger than double bonds. So it's going to be, you're going to have a hell of a time trying to break apart a triple bond, but a single bond or a double bond is going to be easier. All right. So you don't need to know necessarily the lengths of them for a test or anything. So when writing these Lewis structures, because all of these things are this, not that, but this down here, this is known as a Lewis structure. It's showing you where the atoms are in relationship to each other and how they're connected to each other. So how do we do that? Well, the system goes like this. First thing you want to do is write the correct skeletal structure for the molecule. And the skeletal structure is you just want to put the atoms like in an appropriate way. So the skeletal structure shows your relative position of the atoms. In nature, usually oxygen is a central atom and hydrogen acts as what's called a terminal atom, or it's at the end. Why do we put hydrogen at the terminal atom? So if we look at like water, for instance, why would we put hydrogen on the sides? One reason, hydrogen only wants 2 electrons. It just wants a duet. So if I was to put the hydrogen in the center, it would have access to too many electrons. It wouldn't be happy. So hydrogen, keep on the outsides. Really the only way to know the correct skeletal structure is to examine it in nature. We're not going to be doing that. We're just going to be sort of guesstimating. So a couple guidelines, hydrogen atoms will always be on the ends. Molecules tend to be symmetrical. So when you have several, a molecule containing several atoms of the same type, those tend to be on the outside. Are there exceptions? Of course, there's always exceptions, but I'm just going to be going off of those things. So like, let's say we've got, so we already kind of know what the structure for water is, but we'll go through it anyway. So I've got H2O, and then also let's do CCl4. So when looking at this structure, if I was to make the skeletal structure, hydrogens like to be on the end anyway. So I'm going to put oxygen in the center and hydrogen on the side like this. I would never go HHO with this being in the center. It would have too many electrons, and that doesn't look very balanced and symmetrical. Nature, things like to be balanced. So we're going to keep it at this. This one over here, CCl4, when you have multiples, those usually are on the outside. So carbon I'm going to put in the center, and then I'm going to put the chlorines around the carbon. Okay, and that creates something that's somewhat symmetrical. So the next thing that we need to do when drawing these structures is to calculate the total number of electrons for the structure by summing all the valence electrons together. So how many electrons do you get to distribute? Do you get to move around? Do you get to play around with? You don't just get to like randomly pick. So when we're looking at these two things, it's not like I'm like, well, I'm just going to put electrons until everybody's happy. No, you only get to use how many electrons are brought to the table. So hydrogen always brings one valence electron because it's in column 1. How many of them do I have in this molecule? I have 2 of them, so I need to multiply that by 2. I add it to whatever the oxygen is going to bring. So oxygen is in column 6, so it always brings 6 electrons to the board. And there's only 1 of them, so we just multiply by 1, for a total of 8 electrons. Okay, so when I do my structure, I have to have 8 electrons. Don't get confused on how many electrons are being brought and how many electrons they want. The number of electrons they bring to the table is based off of the column they're in. How many electrons do they want? They always want 2 or 8. The hydrogens want 2, everything else wants 8 or an octet. So let's add up these valence electrons. Carbon is in column 4, so it brings 4 valence electrons, and there's only 1 of them, so times 1. Plus chlorine. Chlorine is in column 7, so it brings 7 valence electrons, and there are 4 of them, so I need to multiply that by 4. So that's what, 28 plus the 4 is 32, a total of 32 electrons. So quite a few electrons that need to be on the board. You don't get to change those numbers. Okay, once you've calculated you need 8 electrons, there better be a total of 8 or 32 for this one. So the next step as we go through this, it is important to note too, if there's a Lewis structure, so for a polyatomic ion, so if you're doing it for, let's say, sulfate, you have to increase or decrease the number of electrons based off of its charge. So if it has a -2 charge, you have to actually add 2 electrons. If it has a +1 charge, you have to subtract 1 electron. In general, you should end up with an even number of electrons. So if you're calculating these and your electrons are not an even number to give you like even pairs, you've probably calculated something wrong. Okay, the next thing is to distribute the electrons among the atoms, giving octets and duets to hydrogen to as many as possible. Begin by placing 2 electrons between each pair. This is the minimal number to make a bond. Then distribute the remaining electrons first to the outer guys, then to the inner guys. Again, I think it's just easier to go through an example. So we've established, right, that this is a molecule. Like I've told you, it's H2O. So it has to be stuck together. So the most basic way you can stick something together is a single bond. So I'm going to do that. I'm going to stick this thing here and I'm going to stick this thing here together. Otherwise, it wouldn't be a molecule if it wasn't stuck together. Then after you've stuck it together, you don't do double bonds, you don't do triple bonds, you do none of that until every electron is on the board. So I need to get the rest of my electrons somewhere on the board. You always want to fill the outer guys first, and then if you have leftover, work to the inner guy. What do these lines represent? Remember, each line is 2 electrons. So at this point, I have used a total of 4 electrons. But how many do I need? I need to have 8 electrons on the board. So I need to put 4 more electrons on the board. Do I want to put the electrons here? No. Why don't I want to put them on the hydrogen? Well, look at hydrogen is already happy. Hydrogen likes, remember, hydrogen likes a duet. So it's got access right now to the 2 electrons in the pair. It's good. How about this hydrogen? It's also good. So where am I going to put the remaining 4 electrons? I'm going to put them on the oxygen. One set here and one set here. After that, what do you want to do? You want to check and make sure that everybody's happy. So the hydrogens are happy, they have duets. The oxygen is happy because it has an octet. Let's count it out. Even oxygen has 2, 4, 6, 8. Okay, all happy, all good. And we have used 8 electrons. If you drew yours like this, oxygen, hydrogen, hydrogen, and you put it like this. Thank you. If you drew yours like this, that is okay. This is a 3-dimensional structure, so it can rotate around. So when I see this structure versus this structure, this is like seeing it from the side for me. This is like seeing it from above. Okay, so don't worry about that. What I don't want you to do though is something like this. We'll do it in red so that we know not to do it like this. Oxygen, hydrogen, hydrogen, and you put like 3 electrons on one side and 1 electron on the other. That doesn't work. These need to be paired off. Okay, so this thing, we don't want that there. We want it here. So let's look at that other one and kind of follow the same system. So we've got our skeletal structure, and we know how many valence electrons we get to play around with. We have 32 electrons that we have to have on the board. So the first thing is to stick it together. So let's make a single bond, a single bond, a single bond, and a single bond. Then I'm going to make the outer guys happy first. So this chlorine, how many does this chlorine currently have access to? As far as electrons are concerned, it only has access to 2 electrons. How many does chlorine want? 8. Yes, it brings 7 to the table, but it wants 8. That's why it's making this structure so that it can have an octet. So if it's got 2, but it needs 8, I need to add 6 more. So I'm going to add 1, 2, 3, 4, 5, 6. And if you're wondering, wow, is she going to really count all those dots up, or does the system really count all those dots up on Mastering Chemistry? It does. So make sure you're putting them correct spots. Then we just kind of repeat this for all the chlorines because they're all going to want the same thing, right? This chlorine wants an octet too, so I'm going to add 6. This chlorine is going to want an octet. And this chlorine also wants an octet. So let's check and make sure all the electrons are on the board. Are there 32 electrons? 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. Correct. 32 electrons are on the board. So we've used all of our electrons. The last thing we want to do is make sure everybody is happy or receiving the octet or duet that they desire. So the chlorines are obviously receiving an octet. That's why we gave them 6, right? We went through that process. So the chlorines are good. We really just need to check the carbon. Does carbon in this situation have access to 8 electrons? It does. 2 from here, 4, 6, and 8. So everybody is happy and balanced. We've created octets and duets where we've needed, and we've used all of our electrons. I think in the slides, the last thing it says is like, if any atoms lack an octet and you can't add any more electrons, that's where we add a double or a triple bond. So I'll show you how to do that one. Let's look at CO2. So CO2. So all I want you to do right now is make the skeletal structure and count up the number of valence electrons. All right, I'll give you just a minute for that. So where do the carbons and oxygens go related to each other? And how many electrons do you have to play around with? We won't stick it together just yet. Okay, so let's, I mean, you can either draw the skeletal or calculate the valence electron. I actually usually calculate the number of electrons I get to play around with first. So number of valence electrons. Carbon is in column 4, so it brings 4 valence electrons. And there's only one of them. We're going to add that to what oxygen brings. Oxygen is in column 6, so it brings 6 valence electrons, but there are 2 of them, so I do need to multiply it by 2, right? Each oxygen will bring a total of 6. So that's what 12 plus 4 is 16. So we should have 16 electrons for the number of valence electrons. Any questions on where that came from? You can unmute yourself and ask. You can put it in the chat. I want to make sure that you are able to calculate these numbers. Give it 15 seconds or so if anybody has any issue on where those numbers are coming from. Okay. So the next thing is to draw a structure that is symmetrical, that follows any sort of octet duet limitations. So both of these things are going to want octets. So as far as what goes in the center, either could go in the center, but to create symmetry, we're going to put carbon in the center. And then we're going to put the oxygens on the sides. So now we need to, I mean, because it's a molecule, it's got to stick together. So let's stick it together with a single bond. So I'm going to stick it here, and I'm going to stick it here together. First thing. Next thing is to make the outer guys happy. So we want to work to make the oxygens happy, and then we can do carbon. So oxygen, it brings 6, but it wants 8. So I'm going to add 6 more electrons here. It has 2 currently, but it wants a total of 8. So let's give it 6 here. And then this oxygen over here also wants the same thing. So I'm going to give it another 6 electrons. Always kind of be mindful of how many electrons you've got on the board. So right now I've got a total of 16 electrons on the board. I have used all of the electrons possible. I cannot add more electrons. So I'm going to do this in red. What I tend to find is students will go, okay, great. So I've got oxygens are happy. Now I need to make carbon happy. He only has 4. So I'm going to add 2 more electrons, or rather 4 more electrons, 2 pairs. Why can't you do that? Well, because now you've just increased the number of electrons to 20. We can't have that. We have to stay with 16 electrons. So the only thing that can happen here, because carbon is short 4 electrons, is that these oxygens have to give some of their electrons to the party. All right, so these electrons here need to get dropped into the bond, or we can make a double bond. You only ever make double bonds once every electron is on the board. If you try and make double bonds and triple bonds and you haven't gotten all the electrons on the board, it's not going to work out. So first fill all the electrons on the board and then start to consider double or triple if needed. So this carbon is getting closer to being happy. It's got 2, 4, 6 electrons, but it's not quite there. Could this oxygen over here share another set of electrons? Like, could this go away and we make a triple bond? I mean, I guess we could, but that makes it pretty lopsided. So instead, what I'm going to do is take another set of electrons from over here and make a double bond on the other side just to create something that's more balanced. Whenever you do double or triple bonds, because you have to erase some things and draw some things, it can mistakenly, you can throw off the number of electrons. So you always want to recount. So do we still have 16 electrons on the board? 2, 4, 6, 8, 10, 12, 14, 16. All right, good. We still have 16 electrons. Is everybody happy? Well, these oxygens here have access to 8, 2, 4, 6, 8, 2, 4, 6, 8. And then what about carbon in the center? He's much happier now. 2, 4, 6, 8. Everybody has access to 8 electrons. Any questions on that? I mean, outside of, we're going to do a little bit more practice on them. Any questions on like where this is coming from? why you're making double bonds. You end up making double bonds and or triple bonds because there aren't enough electrons to give everybody what they need. So they have to share a little bit more than they already are. If you try and fill the inner guy first before the outer guy, it will throw you off. It makes it much more difficult. So always fill outer and then inner. So we pretty much did structure. All right, let's do cyanide. So cyanide is a polyatomic ion, Cn, with a minus charge. There's only 2 of them, so they're just going to be next to each other. So the structure is going to look, here's a C, here's the N. Okay, I want you to do the rest. I'm going to give you about 3 minutes. You need to calculate the number of valence electrons. You need to distribute them and make octets everywhere where it's necessary. This is a polyatomic ion though, so do notice the charge in the upper right-hand corner. That tells you have 1 additional electron. So I'll give you just a couple minutes for that. Okay, so this one is a little funky, but carbon brings 4. There's only 1 of them. Nitrogen brings 5, and there's only 1 of them. Now, if you were to go ahead and calculate this out, you would have 9 electrons. Anytime you get an odd number like that, like at least on an exam, you've done something funky. So recheck or look at the charge. This charge here tells you that you have an additional electron. So I'm going to add 1 electron. So you should have a total of 10 electrons. If you had 8 electrons, it means you subtracted the electron. But remember, a negative means you have more electron. So the first thing we're going to do is stick it together. And then I'm going to make one of them, I don't know, it doesn't really matter. I'm going to make the nitrogen happy. Okay, so he needs 6 more. So 1, 2, 3, 4, 5, 6, 7, 8, and then 9, 10. So there's 10 electrons on the board. And nitrogen, for my drawing, it may have been carbon for yours, but one of them is happy, the other one isn't. So what I need to do is move a set or a pair of electrons into a double bond situation. Nitrogen is still happy. He still has access to 8 in my drawing. Carbon has access to 6, so it's getting closer, but it's not quite there. So the last thing we need to do is move another pair over. Are there still 10 electrons on the board? 2, 4, 6, 8, 10. I still have 10 electrons on the board. And have I created octets? Yes, this carbon has access to 8 and this nitrogen has access to 8. And so that would be a situation where we'd need a triple bond. Again, these dots, like wherever they are, it doesn't really matter. You could have put these two here, these two here. You just don't want to have like one here and one over here. Okay. So I'm going to give you a couple of these to do. NH3, NH4 plus, and you may want to save these notes because some of these may be repeats in your lab that you have to do this week. Let's see. What do I want to do? All right, give me a second. Sometimes it's hard to just think of these out of thin air. You start those two and I'm going to come up with another one. All right, so for each, calculate the number of valence electrons, draw a skeletal structure, and then distribute the electrons. Give y'all just another minute, wrap it up. Okay, so the first two look similar to each other, but they're slightly different and they'll have different layouts. NH3, nitrogen will bring 5 electrons, and hydrogen will bring 1, but there are 3 of them. So we should have a total of 8 electrons for this first guy. When drawing it, nitrogen is going to go in the center and then the hydrogens are going to go on the side. One reason is because it creates something symmetrical. Another reason is because hydrogens just want to be on the edges so that they don't have to have more than 2 electrons. Then we need to stick it together. So stick, stick, stick. Do we have 8 electrons on the board? Not yet. I have to have 2 more electrons because there's 6 right now. The hydrogens are already happy just being bonded. That creates their duet. So those 2 additional electrons should go on the nitrogen and we're done. I mean, we'll check and make sure that everybody's happy, but the hydrogens are happy with the bond and nitrogen has access to 2, 4, 6, 8. So everybody's good. We are done. We have the right number of electrons. This one, a little bit different. Nitrogen brings 5. Hydrogen brings 1, but there are 4 of them and there's a plus. Plus means we have a positive charge, which means we actually want to subtract an electron. So you should, in this case, have 8 electrons as well. Okay. I know the plus and the minus and the minus and the plus can get confusing, but think about what this means. It means that we have one less electron than what should be there. If we didn't take that into account, we would have had 9 electrons. That should have been a red flag, something isn't right. So we'll draw the structure with nitrogen in the center, and I'm gonna put the hydrogens on the side. There are 4 hydrogens in this one. Stick it together. Well, that's all 8 electrons. Let's make sure everybody's happy. The hydrogens are all happy, and the nitrogen has access to 2, 4, 6, 8. So it's happy too. The difference between these two being that, you know, this one just has 1 additional hydrogen on that lone pair of electrons. This last one here, we have silicon brings 4, sulfur brings 6, and there's 2 of them for a total of 16 electrons. This is a very similar structure to CO2. You'll start to see repeated patterns with just different atoms. So silicon, there's only 1 of those, so I'm gonna put that in the center. The sulfurs are gonna go on the side. I stick it together. Then I make the outer guys happy, right? So 2, 4, 6, and the 8. 2, 4, 6, and the 8. 16 electrons are currently on the board. Sulfurs are happy. Silicon isn't happy yet, so we have to share some electrons. So we're going to take these and move them here, take these and move them here. When you're doing this assignment, you may want to do it in pencil because you will have to erase. So those will get double bonded. Make sure there's still 16 electrons, 2, 4, 6, 8, 2, 4, 6, 8. 16. Is everybody happy? Yes, everyone is happy. Okay. Have you do one more. This one has a little something funky that happens to it, but you should be able to draw a structure, I think. Let's do SO3. I think that's what it is. Can't remember. Oh, one thing I want to talk about too, before we do SO3, is there are exceptions to the octet rule. So some things will take less. Well, one thing, nitrogen is sometimes okay with like an odd number of electrons. Boron is happy sometimes with just 6 electrons instead of 8. And sulfur and phosphorus, these can have expanded octets. So sometimes they can have like anywhere between 12 and 10 electrons. So we call them expanded octets. I will not be testing you on exceptions. Okay, you may see it pop up in your homework. So you may see SF6 and be like, oh, that has way more than the electrons that we're supposed to have for an octet. You wouldn't see that on a test. All right, everything you're going to see is either going to want an octet or a duet. So with that, let's do not SO3, let's do SO2. SO2. So I want you to do the Lewis dot structure for that. I'm going to give you 3 minutes. Okay, so sulfur brings 6. There's only one of them. Oxygen brings 6, and there's 2 oxygen atoms. So we should have a total of 18 electrons. I'm going to put sulfur in the center and the oxygens on the side. First thing we want to do is stick it together. Stick, stick. Then we make the outer guys happy and then work towards the inner. So this one still lacks 6, so let's add 6 electrons here. This one also lacks 6, so let's add 6 electrons here. How many electrons are on the board? Right now there's 16 electrons on the board and I need 18. So I need to put 2 more electrons somewhere. Where am I going to put those 2 electrons? I'm going to put them on the sulfur. I wouldn't put them on the oxygens because the oxygens are maxed out. So now we have 18 electrons on the board. Are we done? Well, the oxygens are happy. The sulfur is not quite happy. he is lacking access to 2 electrons, right? So I need to make a double bond somewhere. So let's say I could take these 2 and stick them here. That's what I'm going to do. Take these 2 electrons away from that oxygen and move it to a double bond. Are we currently happy? Yes, now we're happy. So this oxygen has access to 2, 4, 6, 8. This oxygen has 2, 4, 6, 8. This sulfur has access to 2, 4, 6, 8. Everybody has 8 electrons, and there are 18 electrons on the board. Now, the reason that this is a little bit different is because if I consider this to be oxygen 1 and this to be oxygen 2, instead of putting the double bond off of oxygen 1, could I have put the double bond off of oxygen 2? The answer is yes. So instead of drawing it like this, I could have drawn it like this, where there's a single bond off this oxygen. Let me add this. And instead of making the double bond here on oxygen 1, I make it off of oxygen 2. All right. So this is known as a resonance structure. Resonance because it's resonating, it's sort of resonating back between these. And it's not that the double bond is actually like hopping back and forth, but it's more like the double bond is sort of half existing in both spots. So sometimes you may see just one of these drawn and then they put like a dotted line here to let you know that like there's a double bond, it's sort of half here and sort of half here, but it's not 2 double bonds, okay? It's 2 half double bonds. We wouldn't draw it like this. Oh, and I'm sorry, let me put the 2 electrons on top there. We wouldn't want to draw it like this. And I see this happen quite a bit where people will say, oh, well, I'm going to erase this and I'm going to erase this and I'm going to put a double bond on both of them. Why doesn't that work? Well, look how many electrons sulfur has access to. 2, 4, 6, 8, 10. Too many electrons here. So only one of the double bonds is happening. So if you ever come to a situation where you could make, where you need to make a double bond, but you only need to make one of them, and it doesn't really like matter which oxygen you put it on, you just have to pick one, that's a resonance structure. So let's do another one of these, NO3 minus, or this is also called nitrate. So the total number of valence electrons in this thing, nitrogen brings 5, oxygen brings 6, and there's 3 of them. And then the minus means that I have to add an additional electron. So I have 18, 19, 20, 24. When I do this structure, I put nitrogen in the center. I put oxygens on the sides. What do I have to do? I have to stick it together, right? 24 electrons means that I make the outer guys happy first. So this oxygen needs 6 added. This oxygen also needs 6 added. And so does this one. How many electrons are on the board? Right now, there are 24 electrons on the board. So we have all the electrons we could possibly use. Oxygens are happy. Is nitrogen happy? He's not happy yet. So we need to make a double bond. Where do we make the double bond? Well, that's a situation where, you know, if we consider this oxygen 1, oxygen 2, oxygen 3, how many double bonds do I need? I only need to make one double bond, right? Nitrogen only needs one more set of electrons. So which one are we going to pull it off of? Well, we could pull it off of here and put those there. Or we could have pulled it off of here, or we could have pulled it off of here. You don't pull them all at the same time. You kind of pick one. So again, sometimes it's drawn with, you know, one for sure double bond. Oh, come on. One for sure double bond. And then the other ones are just sort of like dotted, letting us know, right, that this is sort of resonating around. So we would say that this is a resonance structure. So we can see here, we can have, for that SO2, right, we could have double bond over here, or we could have the double bond over here. A lot of times they'll draw both of them with an arrow in between to let you know that they're both sort of simultaneously existing, or they're intermittent structures. So we're gonna stop there for today. Next time, we're gonna expand this into 3 dimensions. So we're gonna look at how these Lewis structures, because everything we've drawn thus far has been flat, right, on a piece of paper. So we're gonna expand these out and see how they look in 3D. If you have a molecule set, that can be helpful. If you don't, if you have like toothpicks and marshmallows, sometimes that is helpful too, to make it in 3-dimensional shapes. But we will work on that next time. If you have any questions on this, stay around, or any personal questions, stay around. Otherwise, have a good day, and I will see you all on Wednesday. And I will expand out that homework assignment if anyone had issues getting it completed.
Yeah, I had a question about the lab.
What's up?
The page 2, I couldn't find the demonstration for the.
Really? I feel like somebody
Yeah,
else said that too.
Well, I sent you an email, but
Oh, it was you. Okay,
yeah.
That's weird.
I mean, when I went to the data, all I was getting was the one video of the flames.
Let me see.
Same. There wasn't one on mine either. I just had to guess.
What
Right,
was the question asking with
It was
it?
asking for the spectral lines for white light, and let me find it.
So those,
And then neon, yeah.
yeah. So
Yeah, I looked those up in the book. And
yeah, that's
just,
what I was going to say. You would find those you could find them in the textbook, or you could
Okay.
find them online if you just look up like hydrogen spectra. It'll give you where the discrete lines are. So if
Okay.
Elizabeth, if you want to like finish that up and then resubmit it, that's fine, and I can give you full credit for it. Okay.
Okay, so like where on the book, you know, I copied it from the book for all of them except for neon, and I didn't take a picture and send it in yet, but neon has got like a bazillion little lines, so you want,
I know.
yeah. All right,
Yeah.
well, I'll just do that and submit it then today.
Okay, yeah. And then if when I do the lab, I happen to take 10 points off because of it being late, just re-email me and remind me of this exact conversation. Okay.
Okay, all right.
All right,
thanks.
cool. Bye.
so I kind of just drew some stuff together. I don't know if you can see this on mine. Is that sufficient, or do I need to on the neon, or do I need to
That's
resubmit
good.
it?
That's gonna be fine. Yeah.
Okay, I just
That's
threw it
gonna
in
be
there.
fine.
Okay,
Yeah.
this is a lot of lines. Okay.
Yeah, it'll be fine.
Okay, great.
All right.
Thanks. Have a good day.
All right, you too. Bye, Carrie.